As you can see, this is my wall clock, and what I would like to do is build a deep learning model that can read a picture of this clock, analog clock, and predict the time in digital format. Now let's discuss if it is a good problem for deep learning, if it is a problem that's fit for a deep learning model or not. Now, in order to build a deep learning model that can receive a picture of an analog clock and predict time, what I will need is lots of pictures of the of a clock like this with corresponding labels as the time that is currently shown in that picture, and then train the model, hoping that the model will learn to predict the time accurately. Turns out that formulating this problem in such a way for a deep learning model to learn to predict time is not a good fit for a deep learning model. And here's why. The reason is the pictures that we take of various times of the analog clock will not be sufficient, continuous enough, smooth enough for the deep learning model to learn the patterns in the data. Unless we take pictures of every single possible locations of the hour hand and the minute hand, which doesn't make the problem exciting. You're just trying to create a model that serves as a hash table, which is not what we want. If we want the deep learning model to generalize and understand the notion, the idea of the concept of reading time from a clock, then um, with just a few samples, the model does not have sufficient data to learn from. So for that reason, a problem like this, even though a really deep learning model with sufficient data may be able to solve a problem like that, it is a terrible formulation, a terrible problem in terms of using deep learning to solve the problem. Instead, what could we do? For a problem like this, instead, what we can do is take the pictures, and then one way of solving the problem, say even without using deep learning, is take the picture and using some Python code, investigate or like in a sort of loop and check the longest strip of color, the longest, the biggest, the longest length of a straight line that matches the color of the minute hand in the picture, and then look at the orientation of that longest line, and then understand where it is in terms of the angle in the clock. And then do the same thing for the second longest line that gives you the angle of the hour hand. And if you know the angle of the minute hand and the hour hand, you can easily calculate the time. So in other words, you don't even need deep learning to calculate or to predict time from an analog clock picture. So this example is very interesting because deep learning is not like a drilling machine or a hammer that you use everywhere. There are problems where formulating the problem in a particular way makes it either easier for a deep learning model to learn from the data, or maybe even eliminates completely the need for deep learning model. In this case, if we indeed wanted to use deep learning, what we could do is maybe extract the angles from these lines, or maybe get the x1, y1 coordinate of the longest line, x2, y2 coordinate of the longest line, and then same for a smaller one, and then feed these x1, y1 and x2, y2 into a deep learning model to predict time. Then it will be easier for the model to learn the continuous mapping between the XY coordinates of the minute and hour hands, and then the corresponding time. But as he's directly feeding images to the deep learning model and hoping it will learn from the input images is not an intelligent framing of the problem, is not a good framing of the problem. So this brings us to the topic of feature engineering. That is, um, given an input data, it may be such that we can directly feed the input data to a deep learning model, and that might be the best way to frame the problem. But sometimes may also be important that we use some knowledge about the data that only the experts of the data will be able to tell, to aid, to help the deep learning model learn better, more easily with less computational power. And this entire field, this entire area where you um, extract meaningful features using some knowledge of the data before feeding to the deep learning model is feature engineering. Let me show another example that demonstrates the importance of feature engineering.
I'm going to use TensorFlow Playground for this example. Say we have an input data that looks like this, where the data has two classes. The orange color data set is one class, and the blue color data set is another class. And what I would like to do is use a neural network that has two neurons in the first layer and one neuron in the last layer as the sigmoid layer to classify this data set. Now let me run the training once and see how well the model can classify. We can see that these blue points are classified correctly, and these orange points are also classified correctly. But all of these orange points on the other side of this boundary are classified incorrectly. And that's why the loss is not zero yet. The training loss and test loss, both of them are still very high. Now, what we want to do is, let me stop this and reset this. What I would like to do is add two more features to this input data, where the first feature is x1 and x2. Now all I'm going to do is add one feature, which is the square of the first feature, and another feature, which is the square of the second feature. So all I'm doing is adding two more columns to my input data. One is the square of the first one, the other is the square of the second one. And now let's see if adding these two features can improve the classification power of this model. So we can see that the model was able to classify very quickly, and the error, test loss, and training loss are both zero. So this is a very good example where doing feature engineering, that is adding few informative features to my input data, makes it way easier for my model to classify or learn the mapping between the input and the output.